So, did you have any problem that you started or at all, or you haven't started the homework at all or anything?
Honestly, I haven't to look at the specifically because
Oh, that's fine. Don't worry about it.
really difficult since the homework number 4.
Okay, so let's start with 6. So we might have to, just as a warning, if more people show up and they have questions, we have to backtrack, but let me start with the first one. Okay, so we basically have, so again, this is also kind of for people watching. So we have x, which is going to be 1, and we're specifying 1n, and then x1, and then x2, and this is in just Rn by 3, okay? And so we assume that we project y onto, hold on, let me get my notebook. Where's my notebook? Here it is, okay. Okay. So we project y onto the span of x. So the span of x or the image of x. And then we get x2 minus 3x1, okay? And there's some other stuff, but for this first one, we only need really this information. So for A, they say, okay, sorry. They say, show projection of y onto, so instead of the image of x, it's going to be the image or the span, again, they're kind of the same thing, of 1n and x1. Okay, so instead of projecting onto 1n, x1, and x2, we're just going to project onto 1n and x1. Okay, let me zoom out a little bit. So this hint says, let me see what his hint exactly says. So his hint says, oh, does this also like never load for the first time for you? Is it just me? For some reason, whenever I open this, like open up a homework, the first time I load it, like it always is like no, and then the second time it works. Anyway, okay, it's really annoying. Okay, so his hint says for part A, let V equal the span of all these 3 columns, and then V1 be the span of 1n and x1, and V2 the span of x2. Okay, so argue that V1 and V2 are orthogonal subspaces, and then show that if you have orthogonal subspaces, you can write the projection of y onto V as the sum of the individual projections. And then you're basically there, right? Because you'll notice if you have that the span of y onto x1, x1, and x2 is x2 minus 3x1, then if they're orthogonal and then this projection thing is true, then that would clearly mean that the projection of y onto 1 and x1 is just negative 3x1. So really, we just need to show, does that make sense? So really, the first thing we need to show, okay, is, first thing we want to show is that the span of x2 is orthogonal to the image or span, sorry if I'm using them interchangeably, span of 1n and x1, okay? So this is what we want to show, and this will allow us to write, basically this will allow us to write that the projection onto the span of 1, x1, I'm just going to kind of do this quicker, x2 is equal to the projection onto 1 and x1 plus the projection onto 2, x2, and then that would mean that this is equal to x2 minus 3x1, and then this is what we're looking for, would clearly be negative 3x1, okay? So if we can show that this is orthogonal to this, and then prove this projection thing, then we can just answer the problem, okay? So again, this is a little bit tricky, but what you want to look at actually is the fact that we are given, okay, x transpose x inverse, which is equal to 1 over 555 for negative 1, 0, negative 1, 3, 0, 0, 0, 4. Person that just showed up. How do you pronounce your first name again? Is it Rui? I don't want to be rude.
Rui.
Rui?
Oh,
are you there?
I just joined for the
okay.
Next session.
So I just kind of started. This is 6.1. Have you done 6.1a yet? do you have any questions about it?
Uh,
You're muted. I can't hear you. You can put it in the chat if you want. Okay. Do you want me to go over the start of this problem again? Is what I'm asking. Okay, yes. You want me to explain 6.1, 6.5? Okay, so I'm going to start back with A. So I was doing A, so I'm going to go back and explain what I just went over. Sorry. Okay, so we're saying we have that X, which is equal to 1n, X1, and X2, is an Rn by 3. Okay. And the problem says we project Y onto the image of X, and we get X2 minus 3X1. Okay. So that was all given in the problem. And so what they say is, okay, you want to show the projection of Y onto just the image of 1 and X1. Okay, so instead of showing projection onto 1, X1, and X2, we want to show the projection onto 1 and X1. Okay. And so as his hint for this problem, he says, okay, if you can prove that basically the span of X1 is orthogonal to the span of 1, N, and X1, okay, then we can write the projection onto the span of 1, X1, and X2, which again was written up here as X2 minus 3X1, is going to be equal to projection onto 1 and X1, which we want to know, right? Plus the projection onto X2, which is obviously going to be, in this case, X2, right? Because obviously the projection onto something has to be in that subspace. So we know it's projects onto just 1 and X1. It will be the terms in here that include a constant in X1, which is negative 3X1. So that's the hint for this problem. So really what we want to show is that span of X2 is orthogonal to span of 1n and X1. And that will solve A. Okay. So let me know if that was, sorry, I know I had to re-explain that, but let me know if that doesn't make sense. So then how do we do that? Okay. So what we can look at is we are given X transpose X inverse, which is 1 over 55 times this matrix. Okay. So how does that help? Well, sorry, I have really bad allergies. So how does that help? Well, so I'm not gonna, I don't know if I ever solved for X transpose X, but I don't know exactly what X transpose X looks like, but I know for a fact that X transpose X is gonna look like this form. It's gonna be something, it's gonna look like this. It's gonna have constant like numbers here. So I'll write like A, B, C, D, and then it's gonna have an E, and it's gonna be zeros over here. So you can confirm that if you want. Just calculate X transpose X from X transpose X inverse. I think actually you might do that later in the problem somewhere. But let me see if I ever do that, just to be clear. Yeah, I don't think we ever actually solve that. Oh, we do. Oh, no, we don't. Oh, we do. So this is going to be, so you can just solve this, obviously. So this is going to be 15, 5, 0, 5, 20, 0, 0, 0, 55 over 4. So you can just calculate that, just find the inverse of X transpose X inverse. Okay, so what does this mean? Well, what is X transpose X inverse? Okay, so X transpose X inverse, remember, is going to be 1, X1, X2 times 1, X1, X2. Okay, so then the outcome is going to be, this is going to be 1 transpose 1, right? This is going to be 1 transpose X1, and so on and so forth. So obviously it's going to be symmetric. So let me just do the non-symmetric, the upper triangular part. So obviously it's going to be like this. This is going to be 1X transpose X1. This is going to be X1 transpose X2. All right, yeah, doesn't matter. So X2 transpose X2. So obviously it's going to be symmetric. So we don't have to write it again. Okay. So observe that we know what 1 transpose X2 is. Let me do this in red, actually. So this is equal to 0. And this is here, right here, is also equal to 0. Do you see that? So what that means is that, so we have that 1 transpose X2 is equal to 0, and X1 transpose X2 is equal to 0. So this directly implies that 1 as a vector. So to be clear, these all ones are all vectors. I'm just sorry. I'm really bad at writing the vector. Or 1n might be the better way to write it. Let me write that way. So I'm sorry if you want to go back and see it. I know it's the worst when so many different professors have different notation for like 1 vectors. It's like, I always just write 1 and I was like, you'll know if it's a vector or not, but maybe that's not the best idea. So anyway, that means that the 1 vector is orthogonal to X2, right? Because the definition of orthogonality is that the inner product is equal to 0. So if 1 transpose x2 is equal to 0, then clearly 1 is orthogonal to x2. And this again also implies that x1 is orthogonal to x2. Therefore, that implies that x2 is orthogonal to the image or the span of 1, x1. Okay? So that's what we wanted to prove. Remember, we wanted to show this. This is what we just showed. And it's from this x transpose x inverse matrix. Okay, so that's why these things are 0 critically, because we need them to be 0 in order for us to have this sort of breakdown. Okay, so I'm not going to go into how to show that this projection part. I think that's maybe something you might want to do on your own. This projection thing, you just use it from the formula. You can kind of figure it out. It's one of those things that's kind of, you can kind of look up. So that, and then from there, obviously, it's you pretty much gotten the problem. Okay. Any questions about 6.1a? So again, this one's a little bit tricky. You might have done it a different way. I don't know. This is how I did it. So I'm just gonna say it. You might have done it a different way, and that's fine. Okay. Feel free to interrupt if you have any questions. I know this might be confusing. If I'm talking and you have no idea what I'm saying, feel free to say something. There's not many of you, so you got kind of an individual tutoring session here. Okay, now let's look at B. Yeah, what's up?
So the formula projection span 1 and x1, x2 equals to projection 1 and x1 plus projection x2 is, so can I say is this independent here?
What was the question? Sorry. What do you mean independent?
No, never mind. I was confused. So,
okay, so this is true. So this is true if 1 x1 span is orthogonal to the span of x2.
yeah.
That's the only case you can break it up, when you have orthogonality.
Yeah, makes sense.
Yeah.
Thank you.
So I didn't prove this. I don't know if he wants you to prove it. It sounds like maybe he wants you to. He says show that. So maybe you can show that. I'm sure you can find that in a linear algebra textbook or something. It's not like if it shouldn't be very difficult to prove. But I'll let you do that. I don't really want to. Angie, this is 6.1a. If you have any questions about it before I move on, do you want me to talk about it again, or are you okay? You can put it in the chat or you can talk if you want. Either way's fine.
No, thanks. I'm okay.
You're good. Okay. Do you have a particular question you want me to go over? Or
Not specifically.
what's up?
Sorry, not specifically.
Okay. No problem. Okay. So, okay, let's go on to B. So again, B is a little bit tricky, I think. Okay, let's look at B. So this, I think I'm going to probably focus on this 6.1 just because it's really tricky. And then 6.5 is also pretty tricky. Maybe a little bit about 6.4. I don't know if we'll get to the more computational ones. They should be a lot simpler. I just don't think I'll have time. So, okay, so anyway, so B. So we want to find the projection of Y onto the span of just the one vector, okay? And we want to show that's equal to -1, the -1 vector, okay? So how do we do this? Well, first of all, what is the projection of Y onto the span of 1 of n? So we can calculate that as, so let's write out what it is, and then we can kind of see, we can kind of go from there. So the projection of Y onto this is going to be, in words, 1n, 1 untranspose, 1n inverse, these are not i's. I don't know why I wrote all these as i's. I apologize. These are ones. Oh God. Okay, 1n, 1n transpose 1n. I did it again. Okay. Inverse. I apologize if any of these end up as i's. There are ones. There's just ones. I think I'm so used to writing in, it's like identity matrix of n dimension. Okay. 1n transpose y. And we want to show this is equal to -1n. Okay, so what do we know here? Well, we obviously know what 1n is. So this is, let me kind of underline what we know. So in green, in blue. So we know this. We know what this is, right? It's just 1 times 1's added up. We don't know what this is. So this is our unknown. So really this problem is solving for this. Okay, so that's what I'm trying to explain here. So basically this entire problem is trying to say, okay, what is 1n transpose times y? Okay. So just for reference, obviously this is, and then this is going to be 15 because I believe n is 15. So yeah, so this is equal to 15. Sorry. Okay, anyway, so we want to find 1n transpose y. So how are we going to do that? Well, let's go back to what we actually just found previously. So what we found in part A, okay, was we found the projection, I know, sorry, I'm writing this again, but we found the projection of y onto the span of 1n and x1, okay? And we found that was equal to basically, or I'll just write it out. This was equal to negative 3x1, okay? Well, in terms of a different way of writing this, we can say, okay, well, remember that if we let now z, so we remember we said x is equal to 1, x1, x2, okay? And if we let now z just be 1, x1, then this is like this is like now instead of having the data matrix being 1, x1, x2, and we do regular regression, we can say z is equal to just 1, x1 and go through regular regression, right? So therefore we can say, okay, well, we therefore have that the projection of y onto this is equal to negative 3x1. Another way of saying that is, okay, remember that when we do the projection for a regular, so for regular linear regression, okay, we go through this exact same process. We find the projection of y onto the span of x, and what is it equal to? It's equal to x beta hat, right? The projection of y onto x is equal to x beta hat, which is going to be equal to x transpose x inverse, x transpose y, right? So this is in regular linear regression what the projection of y onto the image of x is. So in this case, instead of being the projection of y onto the image of x, it's the projection of y onto the image of z, and we can replace these x's with z's instead, okay? So we just showed that z times z transpose z inverse times z transpose y was equal to negative 3x1. Okay, I know this is getting somewhere. I know this is a bit, okay, which actually is equivalent to saying, so I'm going to write now this on the right side as z times something. So this is actually basically saying that z times z transpose z inverse z transpose y is equal to actually z, right, times 0, negative 3. Because, right, z is 1, x1, so this is 0 times 1 minus 3 times x1. Remember, x1 is a vector. It's not a value, it's a vector. Okay, so why did I just do all this? The reason for that is, remember, what do we want? Okay, let's go back to what we want. We want 1n transpose y. Well, notice that right here, z transpose y is going to be equal to 1 x1 times y, which will really be 1 transpose y over x1 transpose y, right? And then look right here. This is exactly what we want, 1 transpose y, right? So if we can find what z transpose y is, we can answer what 1 transpose y is, and we can find this projection, okay? So that's what we want to do. So remember, we're looking for this. We know this already. We're looking for this. And I'm saying, look, it's right here, the z transpose y thing right here, okay? And luckily, we know more than we think in here because we know what x transpose x inverse is. Sorry, my voice just cracked. Remember, we know that x transpose x inverse is equal to 1 over 55. So let me just write this again. 1 over 55 times 4, negative 1, 0, negative 1, 3, 0, 0, 0, 4. But remember, z is just cutting off the last part. So you can imagine z transpose z inverse is going to equal to, inverse is going to equal to 1 over 55 or negative 1, negative 1, 3, okay? Therefore, again, sorry if this work is messy. Feel free, if you're confused about what I'm doing, let me know. So let's rewrite this expression with everything we know. And we can say, okay, well, z times z transpose the inverse, which I just said is this. So 1 over 55 4, -1, -1, 3. And then remember, z transpose y is a vector, and it looks like this. So let's let this just equal to a and this equal to b. So remember, this is what we're trying to solve for a, okay? So this can be like times ab. And remember, a is going to be the unknown that we want, is equal to z times 0, -3. And then z is actually, I believe it's invertible. So we can actually get rid of, and it's a square. It happens to be a square. We actually can just kind of say that this actually means that 1 over 55 for -1, -1, 3 times AB is equal to 0, -3. And then look at this. We have an expression that's solvable. So this is now solvable. And I mean, obviously, as a hint, I mean, if we go back up to what we need, so remember, we wanted to show that this times this is equal to negative. Well, clearly 1n transpose y is going to have to be -50. Or sorry, this is 1 over 15. So this is 1 over 15. This is 1n times 1 over 15. Well, clearly this is going to have to be -15, right? And then that gives us just -1n, right? So clearly this is going to have to be -15. So I'm not going to go through the math, but we're not going to solve this, but you end up getting that a is equal to -15. Okay, and that gives you your answer. Does that make sense? Does anyone want me to go over any part of that again? Feel free to talk, or if you don't feel comfortable talking, you put it in the chat. I'll wait like a minute for you guys to process. How about if you want? Or you also tell me to scroll up if I need to or anything.
So the 1n transpose y is gonna be -1 over 15, right?
-15, not -1 over 15, just -15.
-15.
Yeah. Because sorry, if you look up here again, sorry, I know it's hard to see a lot of stuff on the screen, but where was I? Okay, if you look up here, right? So this is 15, so then the inverse will be 1 over 15. And so we need 1n transpose y here to be -15.
Great.
This right here is 1 over 15. This is just the 1 over n, and then we need this to be -15. So again, I'm not going to solve it, but this is what you'll end up getting. So a is going to equal -15, but you know, you can enter that into like a matrix calculator. It should work out.
Okay, great. Thank you.
Awesome. Okay. Cool. Okay, if you guys are good with that one, we can move on. So again, I think these two are super complicated. So if you like these, I think that the B was really, really hard, but it's, you know, it's doable. It's just a little complicated. Okay, let's look at C. Okay, so for C, we want to find what is it? Okay, we want to compute the squared length of y squared, okay? So first thing to remember is that you know that this is equal to e squared plus x beta hat squared. So that's just, this is from like the lecture slides, okay? If you want to look at the proof, I don't think you need to prove this. Okay. So we were given I'm trying to figure out. Hold on one second. Oh. Okay, yeah, I don't need to know that. Okay. Sorry. Yeah, sorry. Okay. So then we were given the fact that e comma y is going to be equal to, what is it again? 120. And this actually ends up equaling just e squared because you end up getting, like, things cancel out. Like, again, this is something that should be in lecture notes. Like ey is like e Yeah, because things, so you get E transpose, because it's like, just look at lecture notes. So this is what E squared is. And then for X beta squared, so X beta hat, the length of that squared is going to equal to X beta hat transpose times X beta hat, which is going to be beta hat transpose X beta hat. Okay, so beta hat, remember, you already know. So beta hat is from the original model, and it's just going to be equal to what is it again? 0, -3, 1. Yeah. It's going to be 0, -3, 1. So that's from the fact that the original model is y is equal to x2 minus 3x1. And then x, we already know what x transpose x inverse is. So x transpose x inverse, remember, we know. So again, I'm not going to do this, but we can solve for x transpose x, or x transpose x inverse. You just invert it. And then that will give you, then you have beta hat, x transpose x, and beta hat. And then you can just plug it into this. And that should give you the answer. So you get 120 plus some value, and we complete the problem. Okay. I messed this up. Hold on. No, okay, I think that's right. We should end up getting that it's equal to 1255 over 4. So maybe double check that. Can I check that? My calculator. Hold on. Oh, I don't have that. Well, I have that number. Okay, hold on. Let me. Where's my calculator? Oh, here it is. It will look funny because I still use a calculator, inverse calculator, but I stand by it. Oh yeah, okay, that's fine. Okay. Maybe I shouldn't have said what this means, but you have to show it. Okay. Now let's look at D. So for D, we are doing a test of, okay, so we're basically performing the test of B1, beta 1 equals beta 2 equals 0 at an alpha level equaling to 0.05. So we need to report the p-value. Okay, so basically for the restricted model, okay, so let's do this. So for our, so we have our larger model and our smaller model. So we already know what we're doing for a larger model. So in this case, our null model or restricted model, however you want to call it, I usually call it M0, is going to be basically that y is equal to beta naught plus epsilon. The other way, actually, I'll write it as, just because usually it's written, is I'll write it like as gamma plus epsilon, okay? Now we need to find, okay, we need to find the projection of y onto 1n for this. Remember? Okay, so remember to find gamma hat. So we actually did this in part B, right? The projection of y, right? Yeah, the projection of y onto the span of 1 is going to be this estimated value, right? Because remember, if you're doing this, if you're just predicting y with one value, gamma hat is just going to be equal to the mean of y, right? So it's just going to be equal to the mean of y, which is the projection onto this vector of ones. So gamma hat is going to be the projection of y onto 1n, right? Because that case, that's our only value. And so we already know what it is. We already know it's going to be -1, the -1 vector, right? So then we want to find the residuals. Okay, so we want to find EA. This is the residuals for the residuals for the restricted model, which is going to be the same as visuals above. It's going to be the sum of y squared minus the sum of negative 1n squared. So remember, above we had the fact that y squared is equal to e squared plus, and in this case we said x beta hat squared, but now x beta hat squared is just negative 1n. That's what our estimated value is. So then we can rearrange this to get this, which is what we need to do a model checking comparison. And then we already calculated this before, right? I said we already found this, and then obviously this is just going to be this negative. What's going to be 15. So I'm not going to get into exactly what it is, but then what you end up finding is the F stat, which is going to be, so I won't calculate this for you guys, but it's the sum. It's just this, which again is should be, sorry, I messed it up. A squared minus this. So again, we know this, divided by 2 over this divided by 15 divided by 3. And I won't calculate this for you, but then this is distributed as f of 2 comma 12. And so you can find the p-value that way. So yeah, all you need to do is find the EA of the restricted values. So you already have e squared for the regular model. To find it for the restricted model, it's just going to be this y squared value, which you already have, right? You calculated above in part C, and then this value, which is just negative 1n squared, the length of negative 1n, which obviously would be 15. Calculate it, and then you can just replace it all in. So that is problem 1. So you can see each problem kind of builds onto itself. But any other questions? Any questions about in general problem 1?
I think it's good. Yeah.
You're good. Okay. So I just like to give people a minute to think. Sometimes it's like you think you're ready, but and you don't like need to have a question. Just trying to. I just try not to rush too quick. Okay. So next up, let's skip to number 5 just because someone asked us about 5, and then we can go back to 4 potentially. Okay. So sorry. Let me look at notes for 5. So let me see, because I'm looking at like my things. Let me just make sure it's the same. Okay. Okay, yes. Okay, so we are considering the usual linear regression model. We are saying let lambda be equal to specifically just x transpose x. So this is just to make it a little easier for calculations points. So sorry, not lambda. What is this? This is gamma, right? Yeah, gamma. I know I messed up. I was calling like lambda, the capital lambda, which is like, this. I kept on calling it sigma, which is bad. So this is, I believe, capital gamma. Sorry, if you're watching this on YouTube, comment below how dumb I am. And then we're just going to let sigma 1/2 is just going to be the square root. So this is if you have symmetric positive semi-definite matrices, or positive definite matrices, I think. Or actually, I don't know if they have to be. But you can find like a square root, it's called. And basically what this just means is that gamma 1/2 times gamma 1/2 is equal to gamma. And then in addition, this is necessarily also symmetric. So this is symmetric, just to be clear, this is also symmetric. Okay. So then the A, it says, show that gamma 1/2 times beta hat minus beta is normal. Specify its mean and covariance. Okay, well, before we do gamma 1/2 times beta hat minus beta, let's talk about what beta hat minus beta is distributed as. So as you may remember, beta hat minus beta. So remember, the t-statistic is this. So this is what we know from the t-statistic. It's distributed as normal 0, 1. Or sorry, the square root of this. This is the t. This is like the t-stat. Except the t-stat, sorry, the t-stat is when you replace this with s. But this is something you can prove earlier. This is, I'll say, related to the stack. So obviously, we also can say more simply instead that we can say beta hat minus beta is distributed as normal, still 0, and then you can bring this up, and obviously when you bring something into a variance into something, you square it. This is sigma squared x transpose x inverse. Okay. So then what would gamma 1/2 times this be? Well, obviously it's just any case we have normal distribution. So gamma 1/2 times beta hat minus beta would still be normal. And then it would be obviously gamma negative 1/2 times 0. Sorry, gamma 1/2 times 0. And then you do just like we did before, right? Where you do gamma 1/2 sigma squared x transpose x inverse. And again, it's symmetric. So you just do gamma 1/2 on both sides. It doesn't really matter.
Is it the beta hat minus beta, or just beta hat minus?
For what? Sorry. Oh, you're right. Sorry, it's beta hat minus beta, not beta hat minus beta hat. That's just 0. Is that what you're saying? Sorry.
Yeah.
Okay. Yeah, that was a typo. Sorry. And then from here, okay, well, let's look at this, right? So then gamma 1/2 beta hat minus beta, not beta hat minus beta hat, because that would just be 0. Normal, obviously this is 0. Okay, so something to note here. So I want to be clear. So something to kind of note here is that, so when you have these positive square roots, you can also write, so remember, we basically said that x transpose x is equal to gamma 1/2, gamma 1/2. But we also can say, okay, x transpose x inverse is equal to gamma negative 1/2, gamma negative 1/2. So this is sort of notation. So he didn't really specify this, but this is like something you can do. So if you can do it that way, because you take the inverse, still going to be symmetric. You can, and then you pull out what these things are called, like gamma negative 1/2 and gamma negative 1/2, and they are also the inverses of gamma 1/2, as you can imagine. So this is not the case for all matrices. If your linear algebra is a little rusty, but it's the case for a lot. So this can be sigma squared gamma 1/2, and then gamma negative 1/2, gamma negative 1/2, gamma 1/2. And as you can see, this cancels out. Okay. So hopefully that makes a little bit of sense. If not, let me know. So obviously it's normal 0 sigma squared I. Okay. Or I, sorry, it wouldn't be I n, would it? I something. Okay, I'll just call it K. It doesn't really matter. You can find the dimensions. That'll be your bit of work. Okay, so then B, they're asking, so what is the question again? So they say U squared. Sorry, is that really loud, that car? I'm gonna close my window. Sorry, there's like a car alarm. Okay, sorry about that. So we have that U squared is equal to beta hat minus beta transpose gamma, capital gamma, beta hat minus beta. We want to find the distribution of beta hat minus beta transpose gamma, beta hat minus beta over sigma squared. So sigma squared is as defined before. Okay. So let's figure that out. So observe that this is equal to, okay, beta hat minus beta transpose gamma 1/2, okay, or sorry, just gamma. No, gamma 1/2, sorry, gamma 1/2, yeah, sorry. Times gamma 1/2 times beta hat minus beta. So now remember, this is symmetric. So this can actually be written as, sorry, over sigma squared. So this can be written as beta hat minus beta, or sorry. This can be written as gamma 1/2 beta hat minus beta, this whole thing transposed. Remember, you transpose, you flip the order. So this whole thing transposed, and we don't have to take the transpose of this because it's already symmetric, times gamma 1/2 beta hat minus beta over sigma squared. Okay. Now you can also again write this as, so this is going to be equal to gamma 1/2 beta hat minus beta transposed over sigma times gamma 1/2 beta hat minus beta over sigma. And we know these distributions. So what is the distribution of this, right? It doesn't really matter that it's transposed. So we know that, well, I'll do this one, or sorry, this transpose should be it. So this one we know is distributed as, so this ends up being basically like we write this as like A transpose A, where A is distributed as equal to sigma 1/2 beta hat minus beta over sigma. And we know this is distributed. So we know this top part is distributed as, so let's ignore the bottom part. This top part is distributed as normal, as we just proved before, sigma squared I k. Again, I don't know the dimensions. I'm kind of lazy that way, right? This is what we just proved in A. Okay. Dividing by sigma, again, you divide out this. So then this whole thing would just be distributed as normal zero identity matrix. Okay.
Yes.
Yeah, sorry, I was just thinking. Yeah. So then since A is distributed as normal 0 ik, then A transpose A would be distributed as a chi-square distribution with k degrees of freedom. Okay, because if you have the length of, so A transpose A, which is also going to be written as the length of A squared, where A is distributed as normal, 0, and the identity matrix, then that implies that then this is distributed as sigma squared k, where k is equal to the dimension of A, or is the number, I don't know, the number of rows of A. I'll say dimension of A. And that's again a theorem you got from the slides from class. So notice how we've solved for what this was, and we just divide by sigma to get it standard normalized, and then we can go from there. Okay, and the next question, let's see what the next question is. Okay, so C says, is u squared, so is u squared, which again was equal to beta hat minus beta transpose gamma beta hat minus beta independent of S squared. Okay, so this you can actually use something you've already done. So u squared is a function of beta hat. So remember, this is a constant. So constant, constant, constant. So the only randomness comes from beta hat. Okay, the only randomness is coming from beta hat. That's something to remember, right? Gamma is x transpose x, which is a constant, the x vector. Okay. So therefore, u squared is a function of beta hat. So it only has to do with beta hat. The only randomness is coming from beta hat. And then S squared is S squared. And you have already proven, so this is again, look in the notes. So look at slides or watch a lecture. You just, maybe you already know this, that beta hat and S squared are independent. So that's really all you need to say, is that since beta hat and S squared are independent, and again, I'm not going to go over the proof of that. I probably couldn't jump out of my head, but you can look at the proof in the slides or in the classes. Because those are independent, then you can necessarily say that u squared, which again, the only randomness in u squared comes from beta hat, is going to be independent of S squared. Okay. So if any questions about that, let me know. So then D, okay. So D is asking, okay, show that, show that U squared over P plus 1 S squared is F distributed. Okay, well, okay. Sorry, 1 second. Thank you. Okay. So what's crucial here is so in
Sorry.
C, what's up?
For part C,
Yeah.
so we just need to show like beta hat and S square are independent, and then we are done.
Yes. So that shouldn't be something you have to prove. I think that's already a given. So you might want to look through the slides to see where he's done that. That was a proof I think he did a couple weeks ago.
Okay.
It's like already known. Yeah, yeah. So you might want, I mean, if you want to write down the proof for it, you can, but if not, you don't, I don't know if you have to, honestly. Okay. So to show this is F distributed, so I don't want to, so basically in C, we showed that U squared and S squared are independent. Okay. So remember, we need that. So what was the U squared we said? We never found the distribution of U squared. We found the distribution of U squared over sigma squared. That's fine. So remember, it's going to be it has to be the ratio of two chi-squared distributions. So we show these are independent. So remember, F is going to be equal to some variable. What letter should I use? M, nope, I've used M. L over some degrees of freedom over Q over some degrees of freedom. I'll say 1, 2. And this will be distributed as F of degrees of freedom 1, degrees of freedom 2, and we need L to be distributed as some chi-squared of degrees of freedom 1, and then Q to be distributed as some chi-squared of degrees of freedom 2. So this is the definition of a F distribution. It's the ratio of two independent chi-squared distributions. Divide each of them by degrees of freedom. Okay. So we have, as it was given to you, it was shown as, you should write that, U squared over P plus 1 S squared. So to be clear, I actually should say this. Above, you actually showed that, so sorry, the K that I was using is actually going to be equal to P plus 1. I guess that's kind of relevant. So remember when I was saying, oh, this is, so let me kind of go back up a little bit. So remember I was saying, oh, this is distributed as K. So it's actually K is going to be equal to, in this case, K is going to be equal to P plus 1. So remember I said it's distributed as chi squared K. Well, it's actually distributed as chi squared P plus 1. So then we can say, okay, well, then we have that this is going to be equal to U squared over sigma squared. Because remember, we showed U squared over sigma squared is distributed as that over P plus 1 from this over S squared. Okay. So this is, we're already good, right? We have the degrees of freedom. This is the degrees of freedom 1. And then this is our L. This is chi squared P plus 1. So we're good on the top. The bottom, I'll kind of leave up to you a little bit more. But remember that S squared, so try to look through the notes of what the distribution of S squared is. And actually, you're going to actually divide. So, sorry, I divided by sigma squared. You can't just, I also have to divide by sigma squared over here. So you're going to have to kind of multiply this. So you need to find the basically like, you're going to have to manipulate this a little bit. but look through the notes for what the distribution of S squared over sigma squared is, and you'll find it's scaled. So times some C, I'll say, is going to be distributed as some sort of chi-squared, but you have to figure out what kind of that is. So that's basically what you got to. So this is already good. The top is good. And the bottom, you need to figure out what to scale it by, and then what chi-square distribution is that it is, and you can solve for that. Okay. Any other questions about this one? Okay. Let me briefly talk about the other ones. I might not go as in depth. They should be a little bit easier. So for 6.2, so let's just look at 6.2. 6.2, you're doing D and E. Okay, so what you need to do this is you need to look at the predicted value. So let me find this. Okay, so you're looking at specifically the predicted value of the mean of Y. So you talked about the predicted mean value of Y and the predicted individual value of Y with these certain values. So, and you find a 90% confidence interval. So to remember is that when you have basically a linear combination of vectors, so if you have like, so let's talk about the difference between the mean and the individual. So for the mean, okay, your 90 whatever, I'll say alpha % confidence interval, okay? Your estimate, so this is for the mean of a value. So you're saying, okay, we have Y is equal to beta naught plus beta 1 x1. Sorry, I'll say mu is equal to this. Okay. And we're saying, okay, let's say for beta naught equaling to 1, beta 1 equaling to 2, beta 2 equaling to 3, and we want to find the mean of people who have this setup. Or sorry, nope, that's not right. So sorry, yeah, no, sorry. We have this, and then we'll say, okay, well, we want to find the mean, then the 90%, or I'll say alpha % confidence interval, the mean of people with x1 equaling, 7 and x2 equaling 3. So you need to know what beta naught, beta 1, and beta 2 are. And they say, okay, given these people are, x1, this x value is 7 and this x2 value is whatever, what do we do for the confidence interval? So remember, mu hat is going to obviously just be, so our estimate, so this is our point estimate, is going to be mu hat, which is going to be beta naught. It's going to be 1 plus 2 times 7, obviously, right? Plus 3 times 3, I guess. And that gives our estimate. And then you've already kind of gone over this, but it's going to be basically mu hat plus or minus the t value for 1 minus alpha over t, and then n minus p minus 1 degrees of freedom. And then times the estimated, so the standard error, which is going to be S times, basically, you need X transpose X inverse, and then you're going to have like A transpose and then A, where A is going to be equal to 173. So it's your predicted, it's basically like A is a linear combination of the 3 variables you're using. So you're using linear combination of 1 beta naught plus 7 beta 2 plus 3 beta 3, sorry, 3 beta 2. So therefore you let A be this and you calculate this. And then for an individual estimate, okay, the difference is now Y, remember, is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. So notice how here you don't have the epsilon, but for the true Y value, you have this epsilon value. So your variance, so your estimate of Y hat's gonna have more variability. So again, you use the same A, and most of it's gonna be the same. The point estimate's still gonna be the same, right? Your best prediction is still the mean of those people with that value. It's gonna be mu hat plus, this is all the same. The difference is that now instead of just doing, instead of S, so S, to be clear, is the estimated standard deviation. It's gonna be S, and then you add in basically an extra S, sort of, S squared. So you do 1 plus A transpose X inverse A. Okay, so this is where so then the confidence interval is larger. Okay, so instead of, you add in basically another sigma squared, or in this case, the estimated value of the S squared, because you're now not only dealing with the estimation issues with the beta values, remember the beta out values are random variables, they're estimated. You're also now dealing with the individual variation within Y, right? So you're going to have a larger confidence interval. Okay. To construct an ANOVA table, so I don't know how, I think you can do this in code. So you can just simply create, so put this in and you can just simply create a linear model. So does it say each of them or all of them individually? Okay. So what you can do is, I believe it's fine to do this in R. Has he let you do stuff in R? I don't know exactly sure. But you can, yeah, I think if you have a question about how to make a ANOVA table, you can let me know. It shouldn't be too bad. The next one is 6.3, or it's also this from the book, and they want you to do all of this. So again, for this, you can download the data. So this is going to be an R, so you're allowed to do an R. I don't know if he wants you to do it more by hand or just sort of kind of like actually doing it, but you can, again, just plot Y versus each of the variables. Beta hat is just going to be X transpose X inverse X transpose Y. So you can just create that. If you have the X matrix in R, which is going to be 1, and then all the data variables. So to be clear, make sure you include a 1 variable there. Then you can find beta hat really easily. Again, for the ANOVA table, you've kind of already done that. To find what's the better predictor, what you could do a couple things. So you could look at the significance level, but I think a better way, or you could look at the an ANOVA table for each individual thing, or you could look at the R squared values. So what you could do is you could predict Y from each of the individual values predictors. So just predicting off one of them and see what the R squared value is. So if you get a higher R squared value for one of them, that could be an indication it's a better fit. And then same with E. So which one's the best? So which one do you want to include? One, do you want to include both? So you just look at the fits and see how it ends up. It might end up being that together they're really good. You might also express that maybe one of them is better because you only include one variable. So potentially, I don't know exactly what these will look like, but there's a chance that adding a second variable doesn't affect much. And you might say, oh, you might be overfitting, although I don't know if that would happen necessarily, but it could happen. And now for 6.4, so this shouldn't be too bad. So basically we have that Y is normal 0. It's just distributed normal with identity matrix. Z is as well. And we have U, which is just a combination of Y and Z. So we want to find this joint distribution. Well, Z and Y are independent, so scaling them is actually not going to make them independent. In this case, so it's just going to be the joint distribution will be obviously normal, and you can find the covariance if you want to, but since Z and Y are independent, as you can imagine, the covariance is going to be 0. So you can kind of maybe want to prove this, but calculate the covariance and obviously pull out the matrices, and you're still going to get that 0. And then, you can still have the variances. The rest of these distributions. So again, you need to figure out, they're a little bit tricky, but in general, remember that the sum of squared independent normal variables are going to be chi-squared with the number of things you sum up. However, if you're dividing by something, it will affect the degrees of freedom. So I'm not going to specify exactly, but it shouldn't be too bad. And then this one, so both these are going to be chi-squared for some sort of degree of freedom. And the sum of two chi-squared variables is a chi-squared with their added degrees of freedom. So all you have to do is add together the degrees of freedom. And then E is really similar to D, in which that you have a chi-squared variable and a chi-squared variable. And you just need to divide by the degrees of freedom again. So this will actually be whatever the degrees of freedom end up being is just what you divide by. And then that gives you an F distribution. So I explained for D. Okay, I'm going to stop recording.